Hi everyone, we'll be discussing the albedo effect and how it's important to our climate. So let's get started on what it is and how it works. The albedo is the proportion of incoming radiation that is reflected rather than absorbed. For example, an ideal black body, which is a perfect absorber, would have an albedo of 0, while a perfect reflector would have an albedo of 1. So how does something get better at reflecting rather than absorbing radiation? There are two ways: making it a lighter color and making it smoother. A black object looks black because it absorbs most of the visible light that hits the surface, while a white object reflects most of it and make it look white. Smoother objects also reflect more radiation than rougher objects. Think of a smooth surface cleanly reflecting radiation, while a rough surface reflection is more chaotic and results in more absorption. Color and roughness are therefore very important in determining albedo, since it depends on the ability to reflect.
Let's get on to how all of this relates to our climate. The albedo effect plays a large role in determining the temperature on Earth. This is because of its influence in global energy flows, which is highlighted by the red ring on the diagram. It shows 102 out of the total incoming 341 watts per meter squared being reflected rather than absorbed. This is significant because the reflected radiation remains as shortwave radiation, so it won't interact with the greenhouse gases as their absorption spectra are in the long-wave radiation range. The radiation therefore goes straight back out to space and doesn't get involved with the greenhouse effect. The Earth's overall albedo can be calculated by dividing 102 by 341, which is roughly 0.3. What's responsible for this? Clouds and aerosols are shown in the diagram to play a large role. Aerosols are solid or liquid particles, not including water, that are suspended in the atmosphere. They can reflect radiation directly, but also interact with clouds to make their droplets smaller and make the clouds denser overall. This is called the Toomey effect and makes clouds more reflective, increasing the cloud's albedo. Clouds already play a large role as they can have high albedos and cover a lot of the Earth, about 2/3 at any given time. Moving on to reflection at the surface, snow and ice play the largest role here, with albedos of up to 0.9.
So now that we know what's responsible for the albedo effect on Earth, we can have a look at how it's changing over time. But first, let's consider what it would be like if the albedo effect didn't exist at all. We can use this model from one of our practical classes and the equations from the energy budget at this surface. We found that the surface flux was equal to the sum of the solar flux and atmospheric flux, and that the atmospheric flux was half of the surface flux. After rearranging, subbing for the fluxes, and some more rearranging, we are left with an equation for the surface temperature. We can then find that with an albedo of 0.3, we get a surface temperature of 30 degrees C. Note that the model isn't perfect but close. If we don't consider the albedo effect and set it to 0, we get a surface temperature of 58 degrees C, which is hotter than the highest registered air temperature on Earth. We can be glad that the albedo effect won't suddenly disappear, but it doesn't remain constant over time. We know, for example, that ice sheets build up over the northern hemisphere in the winter and melt down over the summer, which has an impact on Earth's overall albedo. There are, however, more than just seasonal variations at play.
We can get some longer-term variation in Earth's albedo due to positive ice albedo feedback loops. Positive feedback means an effect is enhanced or amplified by its own influence. For ice and albedo, this loop can start with higher temperatures, which causes more melting and less growth. The result is less ice, reducing the albedo in that area, which increases heating and the loop starts again. This can be further exacerbated by other feedback loops, such as the ice elevation feedback loop. Thinner ice is at a lower altitude, where temperatures are higher, which results in thinner ice. These loops, along with climate change generally, are playing a role in current sea ice loss, but they can also work in the opposite direction. Cooler temperatures promote sea ice growth, increasing the albedo there and hence reducing temperatures. Protecting the ice caps and getting this positive feedback loop going will have a great impact on combating global warming. It is, however, not very easy to do. Another way of using the albedo effect to limit global warming is by introducing more aerosols into the atmosphere, which, as previously mentioned, can increase Earth's albedo and result in cooling. This geoengineering, however, isn't simple either, as it has many drawbacks and wouldn't completely solve our climate change issue. We'll find out more about this in later classes, so we'll leave it there. To summarize, these are the main takeaways for this presentation. Firstly, albedo is a proportion of incoming radiation that is reflected rather than absorbed. Aerosols, clouds, snow, and ice are most responsible for Earth's albedo. It will also be far too hot without Earth's albedo, so it's very important. Lastly, there are positive feedback loops which can exacerbate sea ice change. That is all, and thanks for listening.